Welcome back, Science 10. Today we're going to look at polyatomic compounds, formulas, and naming. Last time we looked at ionic compounds, in which we had one metal ion combining with a non-metal ion. Here we'll look at a combination of non-metal ions that come together and form what we refer to as a polyatomic ion. So for example, nitrate consists of one nitrogen and three oxygens bonded together, and overall they have a charge of one negative. Hydroxide is in one O and one H bonded together and have an overall charge of -1. And you can keep going down the list. These are some of the common ones. Phosphate has one phosphorus, four oxygens bonded together, and overall a charge of three negatives. So think of these as elements bonded together. They're one big group or one big set. Okay. If we look at some common polyatomic compounds, here we have the chemistry name, or it's actually referred to as the IUPAC naming system. So IUPAC stands for International. Oops, take my caps lock off. International Union of Pure and Applied Chemistry. So these names on the left are the names that are used throughout the world. Calcium carbonate, for example, that's what would be called in every country, so that scientists and chemists know what is being referred to. Calcium carbonate, CaCO3. And then over here you have what is referred to as common name. So if you're to buy the product in a store, it would likely be referred to as these names up here. So the IUPAC name, you'll recognize some of these names from the ionic compound lesson that we did. So these are the ones that everyone refers to, scientists, etc. And here is the everyday man on the street type name. So calcium carbonate, chalk and building materials, magnesium hydroxide, that is used as stomach antacid. So if you have an upset stomach due to acid buildup, you take that and it neutralizes that. Sulfuric acid is commonly known as battery acid, etc., etc. So you can see the difference there. Now, writing formulas isn't really any different than we had on the ionic compounds sheet. You just have to realize that these are a group of atoms bonded together, and overall they have a charge. So if we look at magnesium carbonate, so you may have to go back in your other booklet there to see what magnesium is. So magnesium is 2 positive. I'll maybe make a sheet that has all of these on one, so you don't have to keep going back and forth. But magnesium, so it has a 2 positive charge. And carbonate, if we look at our master list over here, carbonate, CO3, 2 negative. Two negative here. Now my negative button is not working very well on my computer, so I'll have to steal one from back here. I'll steal that one. So, whoops, ended up moving everything here. So take that negative there. So once again, we're looking at balancing of charges. 2 plus, 2 minus, 1 magnesium ion will neutralize 1 carbonate ion. So 1 to 1. So simply here, the formula for magnesium carbonate is 1 magnesium and 1 carbonate. So again, don't get confused about this 3 down here. Carbonate just consists of 1 carbon and 3 oxygens. So 1 magnesium and 1 big carbonate group. So that is the formula for magnesium carbonate, because it works out nicely. Okay. If we look over here, copper 1 sulfate. So that tells you copper, and it's the +1 version. So we're told what we're using there. And sulfate, SO4, 2 minus. Oops, my native didn't quite work there. That's all right. I'll just have to do it here. For some reason, it always wants to go up there. So if you take a look here, we have 1 positive and 2 negative. So that's not going to balance. So I'm short of copper here. If I have another copper, I'll have a total of 1 plus 1 is 2 positives, 2 negatives. That balances out perfectly. So the formula, once again, is a summary of how many of each we have here. So copper 1 sulfate would be something like this, showing that we need to have 2 coppers for every 1 sulfate, as you can see here. Now it's a little confusing because you see this 4 here and you automatically think, well, we added a 4 there, but realize that sulfate consists of 1 sulfur and 4 oxygens, so that's 1 sulfate, 1 copper, but this little 2 means we have 2 coppers. So usually that's what kids have the most trouble with, is just these groups of ions and the little subscript there. Hopefully through a few more examples we can understand what's going on there. Okay, calcium nitrate. So if you go back to here, your previous booklet, calcium, 2 positive, and you can see it's in group 2, so it's 2 positives. So 2 plus Ca2 plus. So that's that. And then nitrate, if we look up on our negative ion list, nitrate is NO3 minus 1. So NO3. And I'll have to make my negative over here on the side as usual. Okay. So don't get confused. This is only 1 negative. It's not 3 negatives. That 3 is down below here. So we have 2 positives, 1 negative. So of course we're short of negative ions. So we have 2, we have 1, so we'll have to add another one here. So 2 positives, 1 plus 1 is 2 negatives. You can see I need 2 of those nitrates. So in summary, the formula will be CaNO3. And we need to have 2 of those nitrates, so I'll do that. And now this looks a little awkward here. That looks like that's a 32 almost. So to show that this 2 applies not just to this 3 here, but applies to the whole nitrate ion, what you have to do is insert a bracket to illustrate that that 2 is applying to everything that's immediately before it. So this is the common practice to doing that. So 1 calcium, and this 2 applies to everything before it, immediately before it. Which immediately before it? A set of brackets with NO3 inside. So that's how we would apply a subscript to a polyatomic ion and close it in brackets like that. Okay. Beryllium phosphate. We'll have to go back, look up beryllium. So it's a group 2 element again, so it's 2 positive. So Be and 2 positive. Okay. And then the phosphate negative ion. It's right over there, PO4 3 minus. So PO4 with a 3 minus. Oops, I ended up moving everything again. Here, let's grab that. So I can grab that negative without making everything go crazy here. So this is one of the cases, we did a case like this in the ionic compounds one, and it seems kind of difficult. 2 positive, 3 negatives, how are you ever going to make that balance out? And if you're a math person, think of the lowest common multiple. What's the lowest number that 2 and 3 both go into? 6. So to make 6 negatives, I would need just one more PO4. Oh, geez, I keep doing that. Keep moving the wrong thing here. It's a little bit awkward here. Okay, so there we go. Finally grabbed it. So 3 negative and 3 negative would give me 6 negatives. So if I have a few more berylliums here, they're each worth 2 positive. There's one. Throw another one in there for good measure. So you can see 2 plus 2 plus 2, 6 positive. 3 plus 3, 6 negatives. So that is balanced now. And then the formula just summarizes what we just did here. So we have our beryllium and we have our phosphate. Okay, now we need to show that we have 1, 2, 3 beryllium there. So we show that, of course, by putting a 3 here as a subscript. Okay, and we need to have 2 phosphates. So again, it looks something like this, but then, oh my gosh, it looks like a 42 there. So what we have to do is use a set of brackets around the phosphate, illustrating that that 2, the subscript always applies to what's immediately before it. What's immediately before it? We have the phosphate group. So 3 beryllium, Be3. 2 phosphate, PO4, with the 2 on the outside, and then that is the formula for beryllium phosphate. And that really is as complicated as it gets when you have one that has the lowest common multiple of 6. Okay? What I do is I think I'll stop this video here and continue on with the part 2 session. In the meantime, see if you can figure out the remaining 2 here of iron 3 hydroxide and nickel chloride, the formulas for those.